Lock table is a data structure which records the types of lock granted or requested. If a new request is added, it is added at the end of the queue, queue of request data items. You can see in the picture, this yellow one is no request. This waiting for grant, and the black one is granted locks. Unlock request result in the request being deleted, and later requests are checked to see if they can now be granted. If transaction aborts, all the waiting grants or request of transactions are deleted. Lock manager may keep a list of locks held by each transaction to implement this efficiently. Next, we can discuss about granularity. Allow data items to be of various sizes and define the hierarchy of data granularity, where small granularities are nested within the larger ones. For example, see this hierarchy. This is database, and within this area, which is smaller that of that database, and next is files, and finally record. This is a hierarchy. If we delete or if we lock a node which is higher, the lower one automatically locked. Consider this to a transaction. This is a transaction with the deadlock, as the T1 is wait for Y and T2 is wait for X, and T1 has exclusive lock on X and T2 has exclusive lock on Y. So this is a deadlock situation. For preventing deadlock, we said that each transaction logs all its data items before it begins execution, and impose a partial ordering of all data items, and require that a transaction can log data items only in the order specified by the partial order. And we can implement more strategies for preventing deadlock. The first one is wait and time. It's a non-primitive one. Older transaction may wait for younger one to release data item, but younger transactions never wait for older one. They are led back instead. A transaction may die several times before acquiring needed data items. This wait and time. Older one wait for younger one, but the younger one never wait. They roll back. Next one is wound and wait. This is preemptive one. Older transactions roll back of younger transaction, and younger transaction may wait for older one. In wound and wait, younger transaction wait for older one. In wound and wait, rollbacks may more than fewer rollbacks than wait and time. A rollback transaction is restarted with the original timestamp. Older transaction thus have precedence over the newer one, and starvation hence avoided. Next strategy is timeout based schemes. Transactions wait for lock only for a specified amount of time. After that, wait times out and transaction is rolled back. Thus, deadlocks are not possible. This is simple to implement, but starvation is possible. Also difficult to determine good value of the timeout. This is the deadlock prevention strategies: wait and time, wound and wait, timeout based schemes. Next, deadlock detection. Plus can be described as a wait for graph. Uh, Graph with the vertices and edges. V is a set of vertices, all transaction in the system, and E is a set of edges. Each element is ordered. T implies Tj. If T implies Tj is in E, then there is a data graph Ti to Tj, implies that Ti is waiting for Tj to release that item. When Ti requests a data item currently being held by Tj, then edge Tij is inserted wait for graph. This removed only when Tj is no longer holding a data item needed by Ti. The system is in deadlock state if and only if wait for graph has a cycle. Must invoke a deadlock detection algorithm periodically to look for cycle. For further, okay. Next is deadlock recovery. When deadlock is detected, some transactions will have to roll back or break deadlock. Rollback means abort the transaction and restart. More effective to roll back transaction only as far as necessary to break deadlock. Starvation happens if same transaction always chosen as victim. And now we discuss about another concurrency control mechanism, which is timestamp based protocols. Timestamp based protocol. Each transaction is issued a timestamp when it is entered the system. If an old transaction Ti has timestamp Ts of Ti and new transaction Tj is assigned timestamp Ts of Tj such that Ts of Ti less than Ts of Tj. That means the transaction Ti entered at 10 am and the transaction Ts Tj enters at 10:15. Okay, then obviously 10 less than 10:15. That means timestamp of Ti is less than timestamp of Tj. The protocol manages concurrent execution such that the timestamp and determines the serializability order. In order to assure such behavior, the protocol maintains for each data queue two timestamp values. W timestamp, the largest timestamp of any transaction that executed write queue successfully. R timestamp is the largest timestamp of any transaction that executed read queue successfully. The timestamp ordering protocol ensures that any conflicting read and write operations are executed in timestamp order. Suppose Ti issues a read queue. If the timestamp of Ti less than or equal to write timestamp of Q, then K needs a read value of Q. That was already overwritten. Hence, read operation is rejected. Ti is rolled back. If a TS of Ti greater than equal to write timestamp of Q, then read operation is executed. And the read timestamp of Q is set to maximum of write timestamp of Q and the TS of Ti. Suppose that transaction Ti issues write Q. Timestamp of Ti less than write timestamp of Q, then the value of Q that Ti is producing was needed previously. And the system assumed that never be produced. Hence, write operation is rejected. The Ti is rolled back. Next case, if a timestamp of Ti is less than write timestamp of Q, then Ti is attempting write an obsolete value. Right. Hence, the write operation is rejected. And the Ti is rolled back. Otherwise, the write operation is executed and W timestamp of Q is set to TS of TI. Consider this schedule, the timestamp 1, 2, 3, 4, 5. Timestamp protocol guarantees serializability since all arcs in the precedence graphs are in the form. Timestamps smallest transaction with a smaller timestamp implies to transaction with a larger timestamp, and there will be no cycles in the precedence graph. Timestamp protocol ensures freedom from deadlock, and no transaction ever waits, but it may not cascade free or not even be recoverable. You can see what it is. Consider this TI aborts but TJ read n data item written by TI. Okay. TJ must abort. If a TJ had been allowed to commit earlier, then this schedule cannot be recoverable. Further, any transaction has read a data item written by TJ must abort. This can lead to cascading rollback. Then solution is that a transaction is structured such that its writes are all performed at the end of its processing. All writes of a transaction form an atomic action. No transaction may execute while transaction is being written. A transaction that aborts is restarted with no timestamp. Okay. Next is Thomas Wright rule. Thomas Wright rule is a modified version of timestamp ordering protocol, and it prevents obsolete write operations. That means when TI attempts to write that item Q, if TS of TI less than write timestamp of Q, then TI is attempting to write obsolete value of Q, is it? Then rather than rollbacking, it just omit the write operation. And Thomas Wright rules allows greater potential concurrency, and it allows some view serializable schedules that are not conflict serializable. And in this sessions, we have discussed about two types of concurrency control mechanism. One is log-based protocols and the other is timestamp protocols. In log-based protocols, we discussed two types of lock, shared lock and exclusive lock, and three types of two-phased logging protocols. Simple two-phase lock and stricter two-phase lock, rigorous two-phase lock. As we know that locking protocols may lead to deadlock and starvation. And, we see that how we can prevent deadlock, what are the strategies for preventing, and how we can detect deadlock, etc. Then next we see timestamp protocols. What is Thomas Wright rule? Hope all are understand this video. We can see on the video. Thank you for watching.